Hi everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 3, Differentiation, talking about composite, implicit, and inverse functions. Today we are doing a Chapter 3 review, focusing on 3.1 through 3.6. Enjoy today's review. All right, for today we are going to be doing some review on Unit 3, which was on composite, implicit, and inverse functions. Again, reviews do not cover all materials from the lesson, but should remind you of key points. To be prepared, I encourage you to review all the packets and videos from Unit 3. A reminder again that we've had a number of derivative rules from Chapter 2 and that were introduced in Chapter 3 that are all fair game from this test and moving forward. I strongly encourage you to make sure that you are memorizing those derivative functions, especially the product rule, quotient rule, chain rule. This chapter had a lot of inverse trigonometric functions. Those are all things that are worth memorizing and that you're expected to memorize. So get some flashcards, get going on those. Those are really important. But the highlight of this chapter really was the chain rule and really implicit differentiation are the two big topics I'd make sure that you are reviewing and fully understand before you take this Chapter 3 test. Let's get into some practice though. So they're asking us to find the derivative. Our function is h of x is equal to cosine squared of 4x. Now again, when we have this little squared on the trig function, this is implying that this is cosine of 4x all being squared. And so the way that we want to handle this, because we have a function inside of another function, actually there are three layers of functions, something being squared, cosine of some function, and then that inside function of 4x, we have to do the chain rule for this problem if we are going to take the derivative of it. And so we start on the outside. So h prime of x, the derivative of that outside function is 2 times x. So it's going to be 2 times the inside function, 2 times the cosine of 4x. And then we're going to now multiply, so I guess I can change up the color. I'm going to multiply by the derivative of that cosine of 4x. And so the derivative of cosine of 4x is going to be negative sine of 4x. And then I'm going to now multiply by the derivative of just the 4x piece, which is going to be 4. And so altogether, this looks like this is going to be equal to negative 8 cosine of 4x times sine of 4x as our answer for this first problem. And so that is our h prime, our derivative function for this. Good usage of chain rule where we've got three layers for this one. Again, if you're having trouble with these types of problems, I do encourage you to label your f of x and your g of x. What's your outside function, your middle function, and your inside function as you're working through these. But for the sake of the review, I'm going to not show that. Yep, let's do it. So next one that we've got also looks like a three-layer one. We've got the natural log and sort of this implied parentheses that we've got of then a square root function and then an x plus 3. So if I'm thinking just sort of about the layers here, my outermost layer is that natural log function. My middle layer here is my square root function, and my inside layer is this x plus 3. With those in mind, I know that the derivative of the natural log of x, that outer function, is going to be 1. So let's call the derivative dy dx. It's going to be 1 over x. But in this case, our input is going to be the inside of that, so the square root of x plus 3. But then I need to multiply by the derivative of the inside. So the derivative of the square root of x plus 3, or that rule for taking derivatives from Chapter 2, that if we take that derivative, it's going to be 1 over 2 times the square root of x plus 3. And then technically we need to multiply by the inside of that x plus 3, which is just going to be 1. So I'll leave that as is. But this looks like this is going to simplify to be 1 over the square root of x plus 3 times 2 times the square root of x plus 3. Since these have the same radical under them, that's going to multiply out to be x plus 3. So I've got 1 over 2 times x plus 3, or 1 over 2x plus 6 would be our derivative for that function. So the natural log of the square root of x plus 3, if we take that derivative, we end up with 1 over 2x plus 6 for that derivative. Number 3 looks like an implicit differentiation problem. I know that because it's got these x's and the y's and certainly that xy term. Looking at this, I'm going to need to use the product rule here just because I see 10x times the y. And so let's do it. So if we take the derivative with respect to x of that x squared plus 2y to the fifth is equal to 10xy, again, we're trying to identify, which of these match the variable of the derivative that we're taking with respect to. Here, because they match, we end up with a 2x, right? The derivative of x squared is just 2x and the variables match. Then the derivative of 2y to the fifth is going to be 10y to the fourth. But because this y, that variable, does not match with the derivative variable that we're taking with respect to, we're going to end up with this dy dx term there. That's going to be equal to 10x times y. I'll add this sort of parentheses just so we can see it, but product rule 10x times my y function, here is what the product rule is going to look like if we do that. The derivative of 10x is 10, so this is 10 times y, plus 10x times the derivative of y, which is dy dx. So again, what happened here? This was the product. Hey, I can spell product. Product rule. Okay, great. As what we normally do for these functions, we want to collect all of the terms on the left side with dy dx. If it doesn't have a dy dx, I'm going to move it to the other side. So that means that this is 10y to the fourth dy dx minus 10x dy dx is equal to 10y minus 2x. So essentially I subtracted this 2x to the right side, I subtracted this 10x dy dx to the left side. Now because we've got both of the dy dx's on the left side, I'm going to factor that dy dx out. So dy dx times 10y to the fourth minus 10x is equal to 10y minus 2x. The last step here, now that I've factored that dy dx and now that I've got just one dy dx left, I'm going to divide by this 10y to the fourth minus 10x. And so this looks like this is going to be dy dx is equal to 10y minus 2x, all divided by 10y to the fourth minus 10x. Realistically, again, if this were free response section, this would be an acceptable place to end. But, we want to make sure that we're practicing factoring and simplifying as much as we can. I'm just noticing here that each of these terms here appears to be divisible by 2. So I'm just going to quickly, divide out that 2. This is going to give us 5y minus x divided by 5y to the fourth minus 5x. And that would be our final answer. It doesn't look like anything else can simplify for that particular one. All right, next we've got our the inverse cosecant, or the arc cosecant of x cubed. This, again, not only is this an inverse trig function, one of our rules from this chapter, but it is also chain rule because we have this function inside of this function. So a reminder for that inverse cosecant function, that the derivative of that is going to be of the form -1 over the absolute value of x times the square root of x squared plus 1. Now both of these places, and that should be x squared minus 1. So both of these x's that we have here are going to be our input, and when we substitute that in, the input is going to be our x cubed. So what's our derivative? Y prime is going to be -1. This is our side work. -1 over the absolute value of x cubed times the square root of x cubed squared minus 1. And so if we want to try to keep going, we also obviously, by the chain rule, need to multiply by the derivative of x cubed. And so that's going to be times 3x squared. And so if we simplify, this looks like this is going to be y prime is equal to -3x squared divided by the absolute value of x cubed times the square root of x to the sixth minus 1. And similar to what we did in sort of the 3.5 lesson, we can cancel out some of these x's. And so this is going to give me -3 over the absolute value of x times the square root of x to the sixth minus 1. And that is going to be our final answer for problem number 4. Perfect. Number 5, for each problem, let f and g be differentiable functions where g of x is the inverse or g of x is equal to f inverse of x for all x. F of 6, so they give us some values. F of 6 equals -1, f of 4 equals -2, f prime of 6 is 3, f prime of 4 is equal to 7. What is the value of g prime of -1? Since g of x is equal to the inverse of f of x, we know that our derivative rule here, that g prime of x here, is going to be equal to 1 over f prime of f inverse. And in this case, if we're trying to find the derivative at -1, that's going to be written like this: 1 over f prime of f inverse of -1. So how do we find f inverse of -1? Well, we notice here for this first, these two coordinates that they gave us for f of x, if I know for f of x that a coordinate is 6, -1, which they're telling us here, and another coordinate is 4, -2, well, then that means for f inverse, we're going to switch the x's and the y's. That means that there has to be a coordinate of -1, 6 and a coordinate of -2, 4. So here, if I'm finding f inverse of -1, well, we see for f inverse that when x is -1, the output is 6. So this is 1 over f prime of 6. And 1 over f prime of 6, you know, we can see that f prime of 6 from our table right here is equal to 3. So that's going to be equal to 1/3 for our answer for this problem for number 5. Number 6, let f be the function defined by f of x is equal to this given function. G of x is equal to f inverse, where g of -3 is equal to -1. What is the value of g prime of -3? Okay. So if we're trying to find g prime of -3, again, we know that g prime of x is going to be equal to 1 over f prime of f inverse of x. And in this case, we need to find out what f inverse is, and we're trying to find that at -3. So we know that for g of x, which is f inverse, so f inverse, we know that there's the point -3, -1, right? That's what they told us right here, which is the input for the g function, which is the inverse, right? So I know for the inverse that is that. So that means that for our original function, f of x, that's going to be -1, -3. That's interesting. But, you know, given that, let's plug in the values that they're asking us for. They wanted 1 over f prime of f inverse of -3, and we know that f inverse of -3 is going to be -1, so this is equal to 1 over f prime of -1. And then here, I'm going to need to take the derivative of this function and plug in -1. So the function here, that derivative f prime of x is 3x squared plus 3. And so f prime of -1 is equal to 3 plus 3, which is equal to 6. So this looks like that this is going to be equal to 1 over 6 as our answer for this problem. Nice. Let's move on to number 7. Find the second derivative, d squared y over dx squared, based on the given information. Again, this is the second derivative. Keep an eye out for that notation, right? We could have like third derivative if we were to write it like this. Great. So in order to find that second derivative, we need to find the first derivative first. So y prime, aka dy dx, is equal to, in this case, 5x to the fourth, minus, by the chain rule here, right? Because technically this 4 to the x is in the exponent of that e to the x function. By the chain rule, this is going to be e to the 4x, right? Because the derivative of e is itself, the 4x, the inside stays the same, but we need to multiply by the derivative of the inside. So the derivative of 4x is 4. So I'll just rewrite this. This is 5x to the fourth minus 4e to the 4x. That's the first derivative. If we want the second derivative, well, we take the derivative of that first derivative. So that's going to be what? 20x to the third minus, if we take the derivative of this piece again, another 4 is going to come out. So that's going to be minus 16e to the 4x. That would be our second derivative. And again, looking at this, we're using the chain rule that our outside function is e to the x, our inside function is that 4x, that exponent. And so multiplying by the derivative of 4x, that's where this extra 4 times 4 becoming 16 comes from. That is going to be problem number 7. Number 8. This looks like a little bit of an implicit differentiation problem. I see some x's and some y's, and even though the y is by itself, there's still a y over here. So we're taking the derivative here with respect to x. So the derivative of y with respect to x is going to be dy dx. That's equal to 2y times dy dx. And I'll put those in parentheses. Plus the derivative of x, which is equal to 1. We're going to want to get all those dy dx's on one side. So dy dx is minus 2y dy dx is equal to 1. We factor out, we get that dy dx times 1 minus 2y is equal to 1. And then we divide, so dy dx is equal to 1 over 1 minus 2y. That is our first derivative. All right, again, first derivative, yay. How do we take the second derivative? Probably for this one, we could, similar to our 3.6 lesson, we could probably set this up as a quotient rule problem if we wanted to, but it's also easy if we rewrite this for usage of chain rule. Like this is 1 minus 2y to the negative 1 power. Now if I take that derivative, d squared y over dx squared by the chain rule, that's going to be negative 1 times 1 minus 2y to the negative 2 power times the derivative of the inside. Derivative of 1 is 0, but the derivative of negative 2y is negative 2 times dy dx. And so here we would need to substitute in for that dy dx, which we know is this function here, which I'll highlight. We know that dy dx is this 1 over minus 2y, and we're going to substitute that in for this dy dx over here. This looks like that this is going to be equal to negative 1 over 1 minus 2y squared times negative 2 over 1 minus 2y. So if we do that, that looks like this is going to be equal to 2 over 1 minus 2y to the third power. And that would be our second derivative for problem number 8. Number 9, they're asking us to find the equation of the tangent line. Okay, well, again, this looks like an implicit differentiation, so we're going to need, again, the point, if we're going to find the equation of a tangent line, we're going to use point slope form, which is that y minus y1 is equal to m times x minus x1. And they gave us the point. That's nice. That makes it easy. So the question here is, what's the slope? So I'm going to take the derivative of our equation, because we know that the derivative is the slope of the tangent line. And the derivative of that x squared plus 7y squared is equal to 8y cubed is going to be equal to 2x plus 14y dy dx is equal to 24y squared times dy dx. As usual, we want to collect all of the dy dx terms on the left and get rid of everything else and put them on the right. So 14y dy dx minus 24y squared dy dx is equal to negative 2x. We factor the dy dx out, so that's dy dx times 14y minus 24y squared is equal to negative 2x, and then we divide. So dy dx is equal to negative 2x over 14y minus 24y squared. All right, we found the derivative here. Now, though, we want to find the slope. So we know the slope at negative 6, 2. This is our x value. This is our y value. We're going to plug those into this equation for our x and our y here to find out what that slope is. So what is that? So at negative 6, 2, dy dx is equal to, looks like negative 2 times negative 6 divided by 14 times 2 minus 24 times 2 squared. So that's going to be equal to 12 over 28 minus 96. So 12 over 28 minus 96. So 28 minus 96 is going to give us negative 68. So 12 over negative 68. And then if we simplify that, that's going to give us negative 3 over 17. So what do we have? In this problem, we now have the point, which they gave us, and we have the slope. So our final answer for this, if we want to put this in point slope form, looks like it's going to be y minus 2 is equal to negative 3 over 17 times x minus negative 6, so that's x plus 6 for our final answer for problem number 9. That's going to be the equation of the tangent line. Number 10, if x is equal to y squared minus cosine of x, find the second derivative at what looks like pi over 6. So is that pi over 6 comma 1/2 for that? All right, so find the second derivative. We need to find the first derivative first. So, we're going to take the derivative of this with respect to x. That's going to give me 1 is equal to 2y dy dx plus sine of x. Derivative of negative cosine is sine. And so 2y dy dx is equal to 1 minus sine of x. That means that dy dx is equal to 1 minus sine of x divided by 2y. Nice. So I'll highlight this. So that's our first derivative. We'll need that. And here we sort of have no choice. If I'm going to find the second derivative of this function, we're going to have to do the quotient rule. There's no really fancy way I can rewrite this and get around it. So let's get right into it. The second derivative, d squared y over dx squared, is going to be low d high, so 2y times the derivative of that numerator, so negative cosine of x, minus high d low, so 1 minus sine x, times the derivative of 2y, which is 2 dy dx, all over low squared, so 2y quantity squared for that. Nice. We know then, obviously, that we could plug in and find, we could try to simplify this. We could do a couple different things, but since they asked us at a specific value, this is our x and this is our y, we're going to just plug in what we know and then simplify our x and our y, and obviously substitute in for each of these variables along the way. The only thing that we're going to need that we don't currently have is that dy dx at that specific value. So I'm going to just sort of pause and do a little bit of side work right here. I want to find dy dx at pi over 6 comma 1/2. And so if we plug in, that's going to be equal to 1 minus sine of pi over 6 divided by 2 times 1/2. So that denominator is going to be 1. 1 minus sine of pi over 6 is a half. So this is going to be equal to 1/2 divided by 1, which is just 1/2. So here in red, dy dx at that value is 1/2. So I will just substitute in as I work through this. So 2 times our y. Again, the coordinates that we're using are these up here. 2 times 1/2 times negative cosine of pi over 6 minus 1 minus sine of pi over 6 times 2 times 1/2, which is going to be 1, divided by 4 times y squared. Y is 1/2 squared for that. So if we simplify here, this looks like this is going to be 1. If we do cosine of pi over 6, that's going to be root 3 over 2, so negative root 3 over 2. And then we've got a 1 minus sine of pi over 6. Sine of pi over 6, again, is a half. So we have 1 minus a half, which is going to be a half. So I have minus a half here. And then that's being divided by 1. So this looks like this is going to be negative square root of 3 over 2 minus a half, or negative root 3 minus 1 all over 2 as our answer for problem number 10. little bit tougher here just because, we're doing this implicit differentiation and then we're finding the second derivative and then we have to do the quotient rule here and then we're also using trig functions for it. So there are a lot of layers for this problem number 10. This is definitely probably the toughest one on the sheet, but that is it. And that again is our review for chapter 3. Again, I encourage you to go back and look at those lessons that we've done, look at the videos that we've done, and study up on those derivative rules. Chain rule is really important. Implicit differentiation is really important. Good luck to you on that Chapter 3 test, and have a great rest of your day.